Welcome to Linear Systems and Signals and our first real class where we'll talk about sort of what this class is really about at a fairly high level. So we have three words, linear, systems, and signals in the title of the course. And the question is, what do these three words mean? Well, the two big themes I'd like to leave you with for this course is that signals are everywhere and systems are everywhere. So let's start first with signals. Signals are everywhere. So what do we mean by signals being everywhere? Well, what do we mean by a signal? So that's the first thing that we need to address is what is a signal? And what do I mean by they're everywhere? Now, a signal is just a measurement of some kind. So it's measuring a quantity that's sort of varying over time or maybe varying over space. And we have lots of examples of this in technologies that we interact with on a daily basis. So, for example, your phone. The antenna on your phone is sending out electromagnetic waves. That's a signal. It's being sent to a receiver antenna on the cell base station or on your Wi-Fi router. And similarly, it's receiving messages as well. So these radio communications back and forth, those are signals that we measure with the antenna, and then we have to do something with them, like decode them and figure out that this is an MP3 or this is a video, for example. Another type of radio frequency communication are satellites. So satellite communication, via a radio dish on the ground, that's again electromagnetic waves going from the ground to the satellite up in the sky and then back down as well. And even there's a lot of excitement about doing communication systems or communication signaling over power, but even power signals themselves, if you look at the cycles produced by a generator or other power systems components, you will see that those are also signals, and they're signals that we need to analyze. We need to understand if there's sort of high frequency components or low frequency components. And by analyzing and understanding those signals, we can design systems that can help process those signals. Audio is also a signal. So a microphone is recording sound pressure waves coming from the air outside of it, and then it's transcoding those into an electrical signal, which then you can read on your computer or on your mixer. Temperature is a signal. So if you have a home thermostat, for example, it's measuring the temperature at regular time intervals, and that's producing a sequence of numbers, and that is also a signal. And we could try to analyze that. If there are big spikes or something like that in the temperature, something might be going wrong in the house, like it's on fire. Finally, photos are 2D signals, right? They're measurements of optical intensity on the sensor in the camera, measured. So it's measured over space this time, both X and Y space, and we're receiving this intensity. And so this is a picture of the eclipse from a few years ago that my friend Steve took. So some of examples of systems that were brought up in the previous versions of this course that students came up with on their own were circuits. For example, voltage and current signals are signals that you measure when you do basic circuits for PE2, for example. A lot of people mention EM radio waves, such as Wi-Fi or Bluetooth or TV or AM, FM radio. Some people mention multimedia. I mentioned images before, but also video. You can think of video as a signal. And we're going to be talking mostly in this class about one-dimensional signal processing. So maybe not so much with images, although in the lab you will encounter some images. But these are important examples to have in your mind as, well, what does it mean for something to be a high-frequency component in an image? And then a lot of people mention application-based types of signals, so things like in communication systems or in music or event detection, that you have to detect something while measuring a signal, and that's some sort of processing of a signal. In this class, we're going to be looking really at mathematical representations of signals. So a signal is just a function of time. And some people mention specific functions like sine and cosine waves. Those are functions. They're thinking probably about a function generator, which is what you use in the lab. There are other uses of the word signal, which some people usually think of when they think of signals, and these are also signals. It's a good example of why language is sometimes imprecise. So the use of signals such as like codes and encryption and semaphore and turn signals or emojis, these are all signals. They're signaling something, but they're not signals in the sense of these functions, mathematical functions that we're going to look at in the class. If you're interested in codes, however, for example, there is a whole class on coding that Professor El Ruayab often teaches as well. So signals in general, we think of as being functions over time or space. So we're going to focus on talking about things over time, but you should also remember that you can, for example, measure a seismic signal over space. Voltage level over time is a canonical example of a signal. Pressure measurements along a road is so if you have like a car sensors, pressure in the roadbed for detecting cars, that's a spatial signal. And the pixel intensity on a video camera is kind of over space and time if you think about this 2D image and video. Since we're going to focus on 1D images, we're going to call the horizontal axis time. So we're going to be looking at signals as a function of time, and the dependent variable that is the vertical axis on our plots is going to be the measurement. So we're going to be talking about signals fairly abstractly, but it's always important to have some kind of picture in your head. So like a few examples, as I mentioned before, and then you can try to associate concepts we learn in the class back to these original signals or these applications that you have in mind for signals. So that was signals. What about systems? Systems are also everywhere. And systems maybe are a little bit less easy to think about. People think about different types of words when they hear the word system, much like signal. It's kind of overloaded concept in English. But we can think of for this class as systems are things that transform one signal to another, right? So they take a signal, it's a box that takes a signal in and then produces a signal at the output. And we're interested in what is the box doing. So for example, a bass or treble equalizer control in a stereo system, that's a canonical example of a system. It's a system that adjusts the volume levels at different frequencies or different frequency ranges in your audio signal. So if you want to pump up the bass, you would just increase the gain on the bass component of in your mixer. If you want to think about a communication system, the communication channel between the Wi-Fi router, for example, and your phone, that is has complicated physics of electromagnetic waves bouncing off of things, and there's you don't want to go into all of the Maxwell's equations, but you can try to model it as a relatively simple input-output relationship, where the input is what's being sent out by the router, and your output is what you receive at your phone, and that's a communication channel, and that can also be thought of as a system. Going a little bit more abstractly, we can think about the human body, and the retina in your eye is translating light intensity into a neural signal that is a sequence of spikes that are going down your optic nerve. And so we can examine what is the eye doing to process the light signal that's coming in and turn it into an electrical signal of these neural spikes coming out. And another example, I didn't have a picture for it, but if you want to think about robotics or mechanical control, if those are the sort of topics that interest you, a robot arm, a servo, for example, in a robot arm is trying to translate an electrical signal into a movement. So you would, for example, you can measure the trajectory of the robot arm as a 3D signal. It's a multidimensional signal. And then you could, over time, and then you could see how does that relate to the signals coming in, electrical signals coming into the servo. So a lot of examples of systems that have come up in examples brought up by the class are, communications and DSP examples, such as radar, routers, or cellular networks. These are types of systems. People talk about circuit design, so waves in a circuit as a system. The circuit itself there is probably what you mean by the system. A lot of ideas of mechanical systems. So for example, an engine or a car or refrigerator, and we can model those as systems depending on what we're looking at. We could try to model components of those more complicated objects as systems that we then want to analyze using the tools in this class. And abstractly, again, a system is a function which takes inputs to outputs and translates a signal into another signal. So there are a lot of other uses of the word system that we're not going to be talking about, of course, in this class, like operating systems and the solar system and the financial system and others. So a system, again, is a function that maps signals to signals. And so looking at some of the examples of technologies we saw before, a microphone translates air pressure into electrical signals. That's a system. Stereo equalizers translate audio signals into audio signals with different gains on different frequencies. And the servo motor transforms electrical signals to a robot's arm position. So this class is going to focus a lot, especially after the first 3 weeks or so, on linear systems. So if we call our system H, and Y1 is the output with input X1, and Y2 is the output with input X2, then if I take a linear combination of X1 and X2, then I get a linear combination of their corresponding outputs. That's what it means for a system to be linear. And that's a desirable system because it allows us to do what we call superposition. You take a signal and you take another signal, you superimpose them, that is, you add them together, and when they come out, it looks like the superposition of the corresponding outputs. And that's super handy from a mathematical perspective to try and analyze and understand what systems are doing. It leads to a very beautiful theory we'll see of Fourier analysis. So lots of systems are linear, or almost linear. So many systems, of course, are not. So if we do manage to think of a system as linear, we can also think of it in terms of linear algebra. So we can think of signals as vectors and systems as matrices applied to those vectors. And we'll take a look a little bit, we'll dip our toes into a little bit of this, although linear algebra is not a prerequisite for this class. The big abstraction in this class is to take all of these examples. We have audio and radio waves and light sources and all these other physical examples and abstract them away into just like looking at boxes and arrows, looking at block diagrams. And when we can do that, we can do some very powerful calculations and get a deeper understanding of what's actually going on, that's sort of shared behavior that happens in multiple different systems, even though the physics of those systems are quite different from each other. It really gives you another way of thinking about the world. And I think that when I took this class, for me, it really did make me think about things quite differently. It's really what got me into doing ECE. So I hope really for some of you that you really get to it changes your view of the world, or at least for all of you, you can see that there is this other view that's out there that might be kind of interesting to think about as a different angle on things. So I'm calling this like boxes and arrows, or this block diagram view. So arrows in our block diagrams are going to be things that carry signals. So they're like wires and the air, in the case of communication between your phone and the Wi-Fi router, or you can even think about underwater signals. Like if you want to listen to whale songs, the water is the medium. And boxes are systems, and they transform signals into other signals. So we can use these two tools to kind of then stick boxes together to make chains of systems to understand what those chains of systems are doing to an input signal. So for our examples from before, we have a servo mechanism and system that takes a voltage signal to the robot arm position. The human cochlea in the ear takes a sound pressure wave and translates it into a neuronal spike train. And in satellite communication, you have an electromagnetic wave, a radio wave that comes in, goes through the Earth's atmosphere, and is received by your radio receiver, for example, and that's and turns into an electrical signal. So that whole thing is a system. The Earth's atmosphere plus the receiver produces this mapping between wave and an electrical signal. So why does theory matter? I mean, this class is about signals and systems and theory and mathematics and mathematical modeling and analysis and representation of these things. So if we can develop the right mathematical language to talk about signals and systems, we can really do a lot more than we can just by looking at specific examples alone on their own. First off, it allows us to generalize. So a lot of these systems, it turns out that if a system is linear and what's also called time invariant, these systems behave in a very similar way mathematically, and therefore when you implement them, they behave very similarly with respect to their inputs and outputs. So that is to say, all of these problems have a similar structure, so we can sort of get a general solution that works for many different types of applications. And the other thing is keeping it simple by looking at boxes and arrows and analyzing theoretically what happens when we compose and put together boxes and arrows. It helps us keep the thing simple so that we can analyze more complicated systems like multi-step processes. Like for example, when you receive something on a radio frequency, you have to do a whole bunch of processing to it before you can start decoding the bits, for example, if it's carrying digital information. So what is an example of this? So for example, we have sound waves coming into a microphone. The microphone is taking audio and turning it into a voltage signal. The voltage signal goes into a wireless transmitter, which translates the voltage signal into an electromagnetic wave. That electromagnetic wave goes over the air, goes to a wireless receiver system. I'm kind of leaving out the communication channel here, which transforms the electromagnetic wave coming in into another voltage signal. That goes into an amplifier, and it goes into then the speaker, which translates it back into sound waves. So this is if, for example, you had a wireless microphone that you were using, and it had attached to a speaker. This is kind of the chain of systems that this signal from that you're sending out of your mouth gets translated into an audio signal that other people can hear. So just to give a quick rough outline of the course, and I think this will wrap this up for today. We're going to talk about signals and system basics for the first 3 weeks or so. So different signal models, properties of signals, and system properties, and the importance of linear and time invariance. Actually, we're going to talk about linear time invariant systems for another 2 weeks after that. So that's about the first 5 weeks of the class or so. And then we'll talk about analyzing systems, both in sort of continuous time, so a continuous voltage type of, continuous signals, and discrete signals, so things that are measured only at discrete intervals of time, using 2 different transforms, the Laplace transform, which you've probably seen in differential equations, and something called the Z transform, which is the analogous thing that you use for discrete time. And then at the end of the course, we're going to talk about the frequency domain and talk about how you use the Fourier transform to analyze signals and manipulate signals in both continuous and discrete time. And we're going to use the learning objectives for this course to be described, as we go along, so you can sort of keep track of what you're learning. So just a few thoughts at the end. I like to think of the 3-step process kind of as a sort of engineering cycle, which is, I guess, another form of turning things into boxes and arrows. I guess I really do like everything to be boxes and arrows. So suppose you want to solve a problem. First, you should get a model for that problem, a mathematical model or an analytical model that you can kind of take down and do a little bit of pen and paper calculation with, or calculation, with the assistance of a computer. And you want to understand what are the things that you're trying to analyze. Are you trying to minimize the power while maintaining a certain level of signal quality and so on? There could be other things. You want to minimize delay. You want to maximize gain. These are the kind of things that you like to do in your system to your signal. And then you want to analyze that signal, right? You want to be able to try and develop mathematical relationships between, say, power, speed, or delay, and try and then see how you, in the design of your system, can trade off these different components. And then you want to simulate or build your system. So you can either simulate it in MATLAB, or you can build a prototype, and then try and explore those different parameter settings that you've analyzed. Usually there's too many parameters for you to simulate all of them. So you want to be able to do the analysis step number 2, which is what we're going to be learning in this class, to try and simplify your design process so that you only end up having to look at a couple of different promising candidate settings for the parameters. But really, all of these conversations are two-way. So model, analyze, simulate is, the model and the analysis have to communicate with each other. That is, maybe you revise your model after you analyze it. You say, this model is not quite realistic. Similarly, when you're simulating something, you might say, oh, this analysis has made an assumption that can't really work in simulation. So how do I change the analysis to account for that restriction that I have in the simulation? So all of these things, and then once you get the simulation back, you can say, like, well, how does that change how I should think about modeling the system? So this is a really a sort of meta process, and you want to keep all of these relationships between these 3 components, which we're going to be doing in this course. You want to keep these things active. And similarly, you want to keep, as I said before, at the very beginning and again in the middle, and now I'm saying it again, you want to keep a concrete example in your mind. Maybe it's the audio example with the equalizer, or maybe it's the microphone example, or maybe it's the radio frequency communication example, but something that you want to have to keep in mind in the back of your mind to see, well, how does this relate to that type of application? And similarly, if you see an equation that you've analyzed, you want to be able to say, oh yeah, I know how to simulate that. I know how to write that down in some code and then see what it looks like. Because that's the key to really developing a fluency with the material in this course. So that's a quick introduction, maybe not so quick introduction. And I guess moving forward, we're going to get into the weeds a little bit and start talking about signals and then talking about systems. Thanks for listening.